Hi, I'm Mario Graf. This is Natural Language Processing, and today I'm going to talk about collocations with Wald test. Before I start talking about collocations, let me talk about a little bit on hypothesis testing. Imagine you are in a legal trial. Someone is innocent until you have enough evidence that suggests otherwise. In a more formal definition, you have the null hypothesis that corresponds to being innocent. That null hypothesis is going to be H0, and the alternative hypothesis that is the alternative hypothesis that corresponds to be guilty is referred as H1. So if you say that everybody is innocent until you have evidence, until the data tells you that it's very unlikely that you remain innocent, and since it's very unlikely that you remain innocent, you reject the null hypothesis, which is innocent, and you go for the alternative hypothesis, which is being guilty. In a more formal definition, you have a theta space that you are splitting the theta space, the parameter space, into two, theta 1 and theta 2. You want to test whether lowercase theta belongs to theta 0 or belongs to theta 1. That corresponds to the null hypothesis or the alternative hypothesis. There are two. It's important to mention that theta 0 and theta 1 are defined by the user. So this is something that you say that you define how these sets are, the composition of these sets. Theta 0 goes from, there are two types of sets. One is the one-sided test and the other one is the two-sided test. These are the most common tests. In the one-sided test, what you have, for this is an example, is you define theta and you say, okay, theta is it is a set that goes from minus infinity to 0, and theta 1 goes from 0, it doesn't include 0, to infinite. This theta 0 corresponds to the null hypothesis, and what this set is about can be represented with this notation, and the alternative hypothesis corresponds to this notation. As you can see, there are zeros here, and we can change these zeros for a variable, and this we can use, for example, this variable to say, instead of using 0, I'm going to change where I can see, when I see 0 here, to this variable, and the one-sided test can be read as follows. Theta 0 goes from minus infinity to theta 0, the parameter, and then the set theta 1 goes from theta 0, the parameter, to infinite without touching theta 0. The two-sided test, what is in the one-sided test, what one is wondering is whether the parameter that I want to test, which is theta, it's less or equal than 0, or in the other case where we have a variable there, what we wanted to test is that theta is less or equal than the variable theta, than the variable or the constant where theta 0. On the other hand, on the two-sided test, what one is wondering is the null hypothesis to test the parameter theta is equal to a value theta 0, or it is different. There are more ingredients for hypothesis testing. The other ingredients that we are going to use to define it is let x be a random variable, and let's define with this random variable a rejection region R. That means if x belongs to the rejection error R, then we say that we reject the null hypothesis H0. If x doesn't belong to R, then we retain the H0 hypothesis, that is the null hypothesis. R, the set, the region, is defined using an statistic T, and some constant c that it's going to call it a critical value. And x is all the values that can have the random variable x. And so for all the value, what the rejection region is telling us is that we go for all the values that the random variable x can have. We test it. We test all these values with the statistic t, and if the output of the statistic t on the particular value x is greater than c, then it belongs to the rejection region R. The power function with region R, another definition, is defined. We are going to use the letter beta to tell to refer to the power function of the parameter t theta, which is the probability that theta the probability identified with theta that x belongs to the rejection region R. X is a random variable. That is a definition. And the size of that test is the following. The size of it is also a definition. The size of a test is the maximum value, that is the maximum value that can have the power function b, which is in fact a probability, that is the maximum probability that x belongs to the region. But I'm going to spend a little bit of time here. What we are looking, just pay attention to here, what we are going through all the possible values that the theta parameter, highlighting that theta parameter belongs to theta 0. Theta 0 is the set that contains only points that belong to the null hypothesis, that belong to H0. So what this is telling us is that you go through all the points that are true, that make the null hypothesis true. So these are, what I'm trying to be very clear about it is that all these parameters must return true when tested with the hypothesis 0, because we know that it is true. That is how we are defining it. So we look through all the points, we ask all the points that are true, and we say, okay, what is the probability that u point belongs to the rejection error R? And we look through all the points and find the maximum value of that the point that is the most probable that belongs to the rejection error R. Now, so we go through all the points that are positive for the region, are positive for the hypothesis 0, and ask them what is the probability of being in the rejection error, so in the alternative hypothesis. I use this notation, or this notation is being used to tell you that somehow, somewhere in this notation, it is the parameter theta. So it is hidden, but it is there. That is the size of the test. Now, let's go through an example. Imagine we have the null hypothesis is that the parameter mu is going to be less or equal to 0, and the alternative hypothesis is the complementary, which is mu is greater than 0. We have a set of variables, random variables. In fact, we have n stochastic random variables x, that all of them are drawn from a normal distribution with mu, with parameters mu and sigma, and we know the parameter sigma, so that is something that we know. Based on this definition, what we can see is that the set theta 0 goes from minus infinite to 0, it contains the 0, and and theta 1 goes from 0 to infinite. That comes directly from the definition of H0 and H1. The rejection region R is all the points. As you can see here, there are n different points, which corresponds to the n different random variables. And for each one of these draws, so we sample n different points, but we sample all the possible combinations of n points in an infinite space. So we sample of them, and what we are saying here is that all the points that are true for this expression or true for this statement are going to be in the rejection region R. And that is, we are going to test some statistic test on these n points. Remember that x, n, and x1 and so on are numbers at this point, and we test it, and if the output of this statistic t is greater than c, then they are going to belong to R. And the statistic that we are going to test, given that we are interested in mu, the statistic that we are going to test is the estimated mean. We need to use the definition of the power function, which is b, for the parameter mu. And the definitions tell us that it is the probability that x belongs to the rejection region R. So we use the definition, we know this part, and well, this is the definition, and we know the definition of the rejection region R, which is this one, and we can see here that it's the statistic, and we can see that the statistic is we are saying that the statistic, we are defining it as the estimated mean, so we only make a substitution there, and we say that the probability that x, the estimated mean, is greater than c. That is what we are looking for. We can normalize the stochastic variable bar x, and we can normalize it in order to have 0 mean and 1 standard deviation, which is this part. And as you can see, the left hand side of this inequality suffers the same changes that were applied to this stochastic variable. But what we can see here is that this is a normal random variable that is normalized, so it has 0 mean and 1 standard deviation. We can substitute that by saying this is z, which is a normal way of representing a normalized variable, a normalized stochastic variable, and we can we cannot do anything here with it, that it's just an expression because all of them are constants. And as you can see here, we are looking for the probability that a variable that has mean 0 and 1 standard deviation is greater than this number. And this can also be represented using this other notation. So it's 1 minus the standardized normal distribution with this parameter. With this parameter that corresponds to this one. This is just another notation. This is one way of saying that, and we can replace that with this. Now, we are kind of finishing this exercise. The last part that it is missing, we have defined the power function, which is beta, and what it is missing is to know the size of the test. And the size of the test, the definition is, I want the maximum value. I go through all the values that are in the theta 0 that correspond to H0. These are all the numbers that go from minus infinite to 0, and I test all these values on beta, and this is on the function beta, on the power function. I substitute this is a value that goes from minus infinite to 0, including the 0, and I'm going to take the maximum So I'm looking for the maximum value of this. Remember that this is a probability. So I'm looking for the maximum value of all the points that I know belong to the hypothesis, the null hypothesis. And remember that just the equation that we arrived in the last step, which is this one. And as you can see here, if you if you modify mu, you can see that the maximum value that can have this equation is when mu, I cannot highlight it, but okay, that one. The maximum value that can have this equation is when mu is 0. So I indicate this in this part. So the maximum value is when the supreme value of the power function beta is when mu is 0. So if I say mu is 0, then I should have changed here and say mu 0. But I just kind of forget it. And then if it is mu 0, then I can use this notation, replace mu by 0 when I see it. So as you can see, from this point to this point, the only part that it has been changed is when mu is 0. Now it comes another parameter, it comes another variable here, which is the significance level. So I'm going to say, given that this is the maximum value that I can have, I can say, okay, I want the critical value, which is a parameter that I am interested because it is described here. I am interested. It is described here, the parameter c. So I'm just going to keep. I'm going to say that the maximum value, I'm going to refer it as a alpha, and then I'm going to solve this equation. I'm going to solve this equation for C. And now, because I am interested in C, and alpha is a significance level, is a parameter that I can set a value. Normal values of alpha are 0.01, 0.05, 0.1, and it's a significance. It's called significant level. If I solve this equation for C, then I obtain this part, and following what we have seen, that the probability of the estimation of the mean, which is referred as bar x, the probability that bar x is greater than C, that is the power function beta, and we have defined C. C is this part, so we can replace it, and that is what we are looking for. Here it is I was talking too much. I was talking and I was referring to something, and this is what I was trying to find. I didn't find it here. This expression didn't jump. So beta, which is the power function, it is defined as the probability that x greater than C, which means that it's in the rejection region R. And given that we are looking for the supreme, what we are looking for is all the points that we know are in the hypothesis region, in the null hypothesis that belongs to theta 0. That theta 0 is associated with the null hypothesis. We are looking for all the points that are in the null hypothesis that makes this probability as higher as possible. Now we can change a little bit. We can replace, do a little algebra on this equation, so we can have this notation that it's more common, where C is defined as follows, which is the inverse of the probability distribution at the the value that we are looking is 1 minus the parameter alpha, that it is sometimes that it alpha, normal values that alpha achieve is 0.15, 0.01, and so on. Before I move to the next, I mean, this is, we have seen, so far we have seen how to create an hypothesis testing for this problem. And what we have seen here, or what we are, what we can learn from it, is that given this parameter that you are going to say, okay, I want it to be 0.10, which means that I'm going to collect some data, which data I'm going to collect? Well, this is the data that I'm going to collect. So I'm going to draw n points from a distribution, normal distribution. So I'm going to collect it, and then I'm going to compute the mean, the estimated mean. And if that estimated mean turns out to be greater than c, or in other words, if this equation turns out to be greater than this value, and this value can be computed using this expression, which is 1 minus, as you can see, 1 minus 0.01 is 0.99, which is which is a probability 0.99, and since we are looking for the inverse of the cumulative, then it's going to return us a point, a number. Somehow, given that it's a normal, it's something like 2.6, if I remember correctly, or around that number, a little bit higher than 2 point something. So if this expression is higher than this number, what it's telling me is that the data that we have collected is very, very unlikely. Well, the probability that is very, very unlikely that data comes from the null hypothesis, and the probability of seeing that data, if seeing that data in the null hypothesis, is 0.01 or less, depending on the value. So at least we know that it is the probability of seeing that data in the null hypothesis is less than 0.01. And then we are that concludes that information tells us that we can reject the null hypothesis, because it's very unlikely that the data that we have seen comes from the null hypothesis. Another test. This is a test that can be more useful, because in the previous one we are assuming that sigma is a parameter that we know. Normally we don't know the sigma, we don't know the standard deviation. So in this test, in Wald test, what we are going to test is, you have a scalar, you have theta, which is a scalar parameter, could be the mu, but we can estimate, we are not going to use theta as a parameter. What we are going to use is that we are going to estimate theta, as we did with the estimated mean. We are going to estimate theta, and we are referring to the estimation as hat theta. And also we are going to estimate the standard error. So the estimated standard error is referred as SE, hat SE, which is the estimated standard error of the estimated parameter. Assuming that theta is asymptotically normal, so that it is a normal distribution, asymptotically normal, what we can see, what we are going, I haven't discussed what are the null hypotheses and the alternative hypotheses are. So the null hypothesis is that a parameter, a value, theta 0, is going to be equal to the scalar parameter that we are going to test. And the alternative hypothesis is that these two values, or this is the standard, the scalar parameter is different than the theta 0 value. Assuming hat theta, or the estimated theta is asymptotically normal, we can see that theta minus theta 0 divided by the standard estimation is standard error, estimated standard error is approximately normal with a mean of 0 and 1 standard deviation. And the size of the test, the size of Wald test, tell us that we must reject, or that we should reject H0, the null hypothesis, when this statistic, this W, is greater than this value, which is a value that comes from a unit normal distribution, that it's a distribution that a normal distribution that has mean 0 and standard deviation 1, where W has this form. So what it's missing is to know if the size of this test if the size of this test is alpha, and that means that's the significance level. So what we are missing is that we want to test if the probability of this statistic, when it's greater than zeta, turns out to be alpha. And well, we can follow the definition, and the probability of rejecting is, we only need to make some substitutions. So we have the definition of this one. This one is represented, as we can see here, it's represented by this equation or by this expression, and we want it to be greater than c. As we can see, this part is a normal variable. It is a normal stochastic variable. That means that it is a variable that has mean 0 and 1 standard deviation, so we can replace it by c and everything starts the same. One way of looking to this in a different way is just replacing the absolute value and saying that the variable c, the random variable, is greater than the minus c and is less than this part of c. And as you can see here, well, you can imagine a normal distribution. This is the tail that is in the left hand side, and this is the tail that is in the right hand side. So the probability of this is just alpha. Now let's move on to collocations and hypothesis testing. The part that I want, I think I missed here something. Pretty sure that I just missed one here. 1 minus this equation. Pretty sure that I missed it. What I want you to remember is this part, which is this equation, the absolute value of this equation. This is the size of this is the statistic that we are looking for. The statistic that we are interested in is this part. And this part, if this part, the absolute value of this equation is greater than this, then we can reject the null hypothesis with at least a confidence that the confidence is tell us by the significant level. So alpha could be 0.1, 0.01, and so the same reasoning that I just made in a few minutes ago about how to reject the null hypothesis is valid for this one. Now, collocations. As we have seen, or a collocation is two words or a sentence that the sum of the concept that has each individual word, if we sum them, it is not going to be equal to the concept expressed in the sentence or in the expression. So the idea is that we have words, and these words are going to appear together. So the question is whether these words appear together because they are frequent, and so they are going to appear together just because of chance, or they are appearing together because they are related to it. They are related. In order to model this in terms of hypothesis testing, we can say, okay, we are modeling the appearance of two words together. If we know that W1 is not related to W2, then we can say that these events are independent. So we are seeing them together just because of chance. But But if they are not related, so if they are not related, the probability of seeing together can be expressed as the probability of seeing each as the product of the individual probability. That is the definition of independence, and that is the null hypothesis. That is what we think it is a normal way of thinking, in the sense that each word is independent. Of course, in language that is not happening. In language, most of the words are dependent. I mean, you can predict, if I start a sentence, you are going to have an idea which are the following words that can be placed. So these are not independent. So each pair of words is not independent. But normally we can relax this way of thinking and say, okay, what about, I know that formally they are not independent, but what about if they were independent? Let's imagine that they were independent, and let's look for some pair of words that are more dependent than the other. So the null hypothesis that we want to reject is that the words are dependent. So the null hypothesis is that they are independent. So the null hypothesis H0 is that theta, a parameter that we are going to see, that we are going to define, is equal to theta 0, and theta 0 is the parameter that we set and that define the null hypothesis. And the null hypothesis, so it is theta 0, we say that it's the probability of two independent words. So if they are independent, then the probability of the probability of seeing together is equals the probability of the product of their individual probabilities. So this is the null hypothesis. Now the question, I have discussed what about if they are independent events, which is the probability of independence, but and the null hypothesis is this one. So if they are not independent, what does it mean? Well, it means that if we are seeing here an equality sign, if they are not independent, then it is the contrary. So they are not equal. So the probability of seeing together two words cannot be computed using the product of their individual probabilities. So we have just found out which is the H1 hypothesis, or the alternative hypothesis, which is only the definition that they are dependent words. Now that we have we have defined H1, which is P1, the independence part, and we have defined, we kind of keep this part theta indicated here, and we have defined the alternative, which is not equal, the alternative hypothesis that it's not equal to the individual probabilities. We keep saying, okay, we have just theta, we haven't defined what is theta, so the question is, what is theta? Okay, well, theta, as we can see here in this part, and we can see here in this part, is the probability that W1 and W2 comes together. And we rely on Wald test. And Wald test, we cannot compute this. I mean, we can estimate that. So we have a corpus and we can estimate what is the probability of seeing two words together. So we estimate P, that as we have seen it on the Wald test, that we can use a parameter theta, but instead of using the parameter theta, we use a parameter hat theta, that is the estimation of theta. So using the estimation, what it means is that, well, this is the Wald statistic without the absolute values, and we can replace, we know what is theta 0, we know that it's the product of the individual probabilities, and we know that we want the estimation of P, so we refer here as the estimation of the probability of the words together, and we divide it by the standard error of the estimation of the probabilities. And what is this estimation? Well, this estimation is very simple to compute because we only need to count from a very big corpus, the appearance of one of the two words together, and divided that by the number of the bigrams that we just saw. And the probability of W1 and the probability of W2 can be computed as the probability of W1 or W2. We replace this W by the W that corresponds. So the probability of seeing one word is how many the number of times I have seen that word divided by the number of times I have seen all the words, or by the number of tokens I have in the corpus. Now how can we do that? Now we have all the elements. We only need to code them into a program to know to compute all the Wald statistic for all the tokens, all the bigrams that we have in a corpus, and this can be easily done. Imagine that we have all the tokens, which we have all the tokens in this vector, and also it is a dictionary. C1 is a dictionary that has the words or tokens, and also the number of times we have seen those words in the corpus. And we also count the number of bigrams. So this dictionary 1, 2 has the bigrams as a key, as the key, and the value is the number of times that bigram has been seen in the corpus. And we compute the number of tokens, which is n. How many tokens does this number is only it is the number of tokens that the corpus has. We iterate. Let's define this dictionary W, where we are going to store all the Wald statistics for all the tokens, all the bigrams. We iterate for all the pairs, or for all the key values that are in the dictionary C1, 2, and we retrieve the token, the bigram, and we kind of say, okay, it is a bigram, so it's going to be word 1, W1 and W2. So there are going to be two words in there. We iterate for all of them. We compute the probability, and we iterate also for the value, which is the number of times we have seen that token, that bigram. We can compute the probability, so we can estimate the probability of the words together, of the bigram, which is only the quotient of B and N. And we can compute also theta 0, which is the probability of the individual probability of each word. So this is the count for word 1 divided by N, multiply, or it is the multiply by C, the count of word 2, the number of times that we have seen word 2 divided by N. So we have theta 0, the standard deviation. It is important to say that this process of seeing words can be modeled as a Bernoulli trial. So either we see the word or we don't see it. So it's 1 or 0. 1 if I see it, and 0 if I don't see it. That is why it is a Bernoulli trial. And if it is a Bernoulli trial, then the standard error can be computed following this equation that only uses the probability of seeing the words, the estimated probability, and 1 minus the estimated probability divided by the number of tokens in the corpus. And I should have used left arrow. And the statistic, the Wald statistic, is the following. So you have you store the bigram and you compute this part. Now we can run this algorithm and compute all the tokens. Now we can use this. Let me just try it really quickly through this code. Imagine that we have a dictionary that contains all the bigrams in a corpus. So we have these kind of bigrams. We can sum all the values of that is the count, the number of times we have seen each individual bigram. It is a dictionary, so the counts are in the value part of the dictionary. So we have seen all of these bigrams, and with this information, this number is this number corresponds to n. So we can iterate for all the values, for all the bigrams the bigrams, which is k, and also the count of the bigram, which is b, and with that information we can create the probability of the bigrams for each individual bigram. So we can see here the probability of the bigram in the which is this value, and we can sum all the probability that we have just seen, and we can see that there is a small error, and that corresponds to this operation. We remember that we are working with floats, and sometimes there is kind of an no, it is not an overflow, but because all of them are numbers, but there are rounding errors. Continue. Now that we have this information in a dictionary, what we can do is do the same thing, but for the words. In this part of the library, we have a library that can, in this part, have all the bigrams and all the words that are in a corpus. So we extract the words, and we can have the words in a dictionary. Also, the words, each word is associated with the number of times we have seen that word. So the Wald statistic, we can store it in a dictionary, and we follow exactly the code that I just described in the pseudocode 2 slides before. So we iterate for everybody. We iterate for all the bigrams. We split it, word 1 and word 2. We compute the standard error. We compute the probability of word 1. We compute the probability of word 2. And finally, the Wald test for W, which is the bigram, is computed as follows. With all this information, and we can plot the word cloud, we are going to see this part, which is not very informative. Oh, this is too sad. Well, all this work, and it is a word cloud that doesn't tell us anything. And I would like you, before I kind of explain it, let me try to explain why it is not telling me anything. And it is not explaining us anything because if I plot, for example, if I make this plot, which is, I'm going to go through all the frequency of the word, I mean, all the times a particular word appears. So, for example, I collect in frequency 1 all the words that appear only one time in the whole corpus, and compute for all those words the Wald statistic, and then take the maximum value, and I plot it here, which is the maximum value of all the words that have a frequency of 1, and then move to frequency of 2 and do the same thing, and so on, on frequency of 20. So here in this point, more or less, what I'm doing is I'm computing, I'm retrieving all the words that have a frequency of 20 of appearance in the corpus. Then I compute for all not the words, I'm telling words, but I should have said bigrams, all the bigrams that have a frequency of 20, and for all these bigrams I compute the Wald statistic, and then for all the Wald statistics I only take the Wald statistic that is the maximum value, and I plot it here, and what we are seeing is this plot. So what this plot is, and what this word cloud is plotting, or it's plotting, is using the Wald statistic to tell us which of the words, which of the bigrams are more important. The Wald statistic is telling us that of the bigram, of the is the most important one. Does it? Well, it turns out that of the is a very, very frequent bigram, because it is formed by the word of, which is quite frequent, and the word the, which is also very frequent. So this bigram is very frequent, and this plot is telling me if the bigram is very frequent, so the maximum value of Wald statistic is going to be very, very high. On the other hand, if it is not frequent, then the Wald statistic is not going to be so high. So what we have just done is to use all the frequencies to plot to create the word cloud. But in fact, what we did, but without realizing that we did it, we kind of also plot the frequency of the bigram, and it is more important to be frequent than to have a good Wald statistic. So we are kind of looking at the frequency again. That is not good. So okay, this is just the code that explains how to do the plot. So the plot, we are going to store the maximum value of Wald in a dictionary, and what we are doing here is we look at the frequency of the bigram, and if the frequency, and we look at this dictionary, and if we have seen some frequency, then we are going to retrieve that value. If we haven't seen that frequency, what we are going to say, okay, the Wald statistic of that is 0, and if that is 0, we have computed the Wald value here in this line. If this part, which is what the Wald statistic that we have seen for the frequency, for the particular frequency, is lower than the Wald statistic that we have just computed for that frequency, then we are going to replace it, and that's it. That is how we are kind of getting the maximum value of the Wald statistic. So instead of doing the word cloud for all the frequencies, what about if we only look at one frequency? For example, we are going to look only to the bigrams that appear 15 times. So if we look on for the bigrams that appear 15 times, we are going to see something like that. And this is more interesting. Of course, it is not perfect. It is far from perfect. But it is normal, because what we are testing is we are modeling the probability of appearing two words together. So then our null hypothesis is that they are independent, and the alternative is that they are not independent. So we are not testing whether a particular pair of words are collocations. We are testing if they appear together, which is quite different. We can see something interesting. Well, here is a name that is in the books. We see something that is very irrelevant, that most of the books have this token kind of at the end of the part of the book that tells the sentence is something that says, okay, this file should be named 0, and there is a dot here that I'm removing it with the tokenizer, so that the file should be named 0.txt, and that's it. But what about if we edit a little bit the books, and we remove the header and the footer of all the words of all the books, which the header and the footer are common to all the books, and that's why it is appearing this part, this name and this zip, because they are common to all of them, and there are only 20 books, so these combinations are only the frequency is like in 15, 16, and so on, and they are important because these words are not going to be appearing on a traditional writing, but they are appearing on the footer, so it is fine to find them. This tells us that the algorithm is working, but of course it is retrieving garbage, but the garbage we must remove the garbage from what we are submitting to the algorithm. So if we remove this part of the book, then we are obtaining a better word cloud, and it's telling us a little bit more about the books that we are seeing, and we are only seeing the bigrams that has a frequency of 15. For me, this is the end of the presentation. So if you have any question, just send me an email, and I will try to explain a little bit more about collocations using the Wald test.